one of the first phrases that was used was that this is the hardest paleomagnetic project that's ever been devised.
You're listening to the Cosmic Cast. Hello and welcome back to the Cosmic Cast. I'm John Perney-Fisher. I'm joined here as per usual with the lovely Tom Harvey.
Hello.
And the fantastic Marissa Lowe.
Hello.
And this week, all the way from Cambridge, we're joined by Rich Taylor. How's it going?
Hello.
You're in Cambridge as a research fellow, is that right?
That's correct.
How would you describe yourself? As a metamorphic petrologist? As an experimental petrologist?
I would say most of my research is to do with geochronology.
Right, okay.
And most of that geochronology is specialised in metamorphic rocks.
Okay, because you seem to have quite when I was having a brief browse of your publication list earlier, you seem to have quite a diverse bunch of publications and a diverse bunch of research interests.
Yes, that's true. I mean, almost everything that I've been involved in has some element of uranium-led geochronology involved in it. But I've now, both in the UK and in Australia, been involved in a number of different projects, and they've all had their own sort of specific ideas involved with them, some of which is more mainstream geology, things like metamorphic petrology, and also to do with things like ore deposits, and most recently to do with paleomagnetism. So.
Cool. So you were at Cambridge. You mentioned you spent some time in Australia.
That's correct, yeah. So I did my PhD at Edinburgh, and when I finished that in 2009, I got offered a chance to work in a lab in Western Australia, to work in what's called the Shrimp Lab, which is one of the sort of the big geochronology labs in the world, at the Shrimp Lab in Western Australia, and that was a technician role rather than a research role, but gave me the opportunity to have a bit of an adventure and see a different part of the world. So
awesome.
I then lived in Western Australia for about 8 years after that, doing both that role and then research roles following that.
Wow. So how come you moved back to the UK?
Family reasons mostly. So my wife is English as well. We met at university, and we had our first child while we were living out in Australia, and it became obvious that we were leaning towards moving back to the UK for domestic reasons. So when an opportunity came up, and this opportunity came up at Cambridge, we sort of jumped at it and moved back home. Yeah,
that's really cool. I think that's such a nice thing that you can do in sort of the academic world, that you can just move to another country for an extended period like that. That's really exciting. Yes,
to a certain extent, I think that's true. Like it's a very nice life, I would say, particularly what we call postdoctoral roles. So sort of short-term contracts where if you're willing to move, there's lots of those in lots of different parts of the world, and you could take advantage of that to be a kind of adventure. But then obviously eventually life catches up with you a bit, and you want to settle down. And then once you've picked a place to live, it can then it has an element of stress to it, because once you want to stay put, obviously there are less jobs around. But no, it's definitely a good lifestyle. Yeah.
So why is it called the Shrimp Lab? So it's called a shrimp because it looks like a shrimp. Is that right?
I'm not sure if that's entirely true. There are a lot of sea creature jokes associated with those labs. So the shrimp is a SIMS instrument, so a secondary ion mass spectrometer, and the SHRIMP acronym stands for a sensitive high resolution ion microprobe. And so that was a research project at the ANU, so the Australian National University, through the 80s, and then became a commercially available instrument after that. So the lab that I worked in had the first commercial shrimp lab, which was installed in the early 90s, and that instrument, the shrimp, it has been the workhorse uranium-led instrument around the world now, where those instruments are installed for a long time, since the 90s. So.
That is a fantastic acronym, isn't it?
It is.
So there's a lot of other jokes in there as well. So some of the first software to process the data from that was called Krill.
Brilliant.
The data files that came off the instrument, the original ones, were called prawn files, which I'm reliably informed was playing retrospectively around with numbers. I don't know if that's a sort of apocryphal tale, but that's what I've been told. So there's a number of I think even the software that processes it now is called Squid, and so there's everything involved in it is some sort of in joke.
That's fantastic, isn't it? Yeah.
Did you say it was shrimp shaped as well?
Well, sort
is it
of,
like a curved building, or?
So it's a big instrument. So it's what we call a doubly focusing mass spectrometer. So it has a magnet, which is very very large, and another what's called an electrostatic analyzer, which is sort of a big curved energy filter, and those two bits of the instrument are both over a meter in their sort of arc of radius. So the whole instrument itself has a flight path that's something like 8 meters long or something, and it fits in a kind of U-shaped curve. So it does look a little bit like a curled up crustacean of some kind. But it's a big instrument. It does take up a significant amount of space.
Cool. I mean, that must be quite exciting working in such a pioneering lab like that, I guess. So how hands-on were you in terms of operating and sort of fixing things? And
so that first role that I took on when I moved to Perth, working in the shrimp lab, as I said, it was kind of a technical role. And so my job there was keeping the instruments working. So they required maintenance every week. So stripping certain parts of it down and cleaning them and putting it all back together. It also involved setting up the instrument on a daily basis for people's research and making sure that it was operating in a way that was getting people the data that they needed to collect and as high quality data as possible. It involved preparing samples and teaching people how to prepare samples to put in that instrument. But it was a fascinating lab. So the shrimp lab there in Western Australia at Curtin University, which is where I was based, has been famous for analysing lunar samples and also probably most famously zircon grains from the Jack Hills, which is way out in the middle of nowhere in Western Australia. But the reason it's so famous is because the individual mineral grains from the Jack Hills are the oldest things that we have of our planet. So they're about the oldest ones are about 4.4 billion years old. So right from the beginning of Earth history.
That's very cool.
So did you have much experience doing this kind of work before you started there as a technician, say from your PhD or before that?
Yes, that's a good question. So, and the answer is yes. My PhD at Edinburgh was in itself quite an interesting project. So I was doing an experimental petrology project, and experimental petrology involves essentially making fake rocks to understand how real rocks themselves function. So I was making these synthetic analogues for metamorphic rocks to look at how the minerals grow in those metamorphic rocks, specifically the minerals that we use for geochronology, so the minerals that contain a little bit of uranium that we can use for uranium lead dating. So I was growing sort of fake versions of those minerals to look at how they grow in relation to other minerals themselves. And that didn't just get me involved in uranium lead dating, but specifically to be able to analyze those samples got me involved in this particular type of analysis. So SIMS analysis, using a different set of instruments, not a shrimp instrument specifically, but instruments that are very similar to that and designed in a similar way. I was using those at Edinburgh to analyze these synthetic rocks, rocks themselves. So I did, having not actually been specifically involved in uranium lead dating, I had a lot of experience on the type of instrument itself. Yeah,
I guess we've not really talked on this podcast too much about uranium lead dating before. It might be worth talking about why it's such a useful and important geochronometer, particularly for metamorphic. I guess it's very robust, isn't it? I suppose to.
Yes, that's right. And so uranium lead dating really focuses on what we call accessory minerals. So there's a lot of major rock-forming minerals that everyone's very familiar with, so quartz and feldspars and garnet and things like that, the sort of visible minerals that we see when we look at a rock sample. But hidden away in our rocks, there's what we call accessory minerals, which are usually tiny. They're quite often not visible to the naked eye, but they soak up all the elements that don't fit into those main rock-forming minerals. And most importantly, some of these accessory minerals take up a little bit of uranium. And so one of the ones that we use the most is the mineral zircon. And the mineral zircon takes up a little bit of uranium in its structure when it forms, but it doesn't take up any lead. And so when it first grows, it's got uranium in it, but no lead at all. And then over time, as that uranium decays, the amount of lead in the zircon starts to increase, and we can then use that uranium lead ratio to work out how old the zircon grain is. And then sort of by proxy, we can use that to work out how old the rocks are or any geological processes that happened. And one of the most the sort of key aspects is that zircon itself is what we call an ultra-stable mineral. So it's physically very tough and chemically very tough. So it's very hard to get rid of. Yeah. So once it's grown and recorded a geological event, it tends to survive even from the very beginnings of Earth history, even from places like the Jack Hills, where it's recording, the very beginning of time as far as the Earth is concerned. They're tough enough to survive all the way from those sort of depths of deep time.
Yeah, because I guess the Jack Hill zircons are in sediments, aren't they?
They are. That's right. So as I said, the record of zircon grains from the Jack Hills goes back to 4.4 billion years old, but the rocks at the Jack Hills are only 3 billion years old. So they're sediments. They're if you assume that we can use modern analogues to interpret old rocks, then it looks like a river delta or something like that. But that river delta sediment is full of the eroded remnants of other rocks, as you'd expect from a sedimentary rock. And by using the zircons that are in there to date how old those eroded rocks were, we can see that the original igneous rocks, so the hard rocks that were eroded into that sediment, are far older than the Jack Hill sediment itself, and are in fact from rocks that just don't exist anymore. They've been entirely eroded away, and the only evidence for them is in the Jack Hill sediment.
Yeah, I mean, it's really cool to think that these sort of processes can preserve such old rock.
So the Jack Hills is unique in terms of its record of the early Earth. So if we imagine all of Earth history going back 4.5 billion years, the very earliest period of Earth history we refer to as the Hadean. So it's supposed to be like Hades, the god of the underworld, surrounded by fire and brimstone. And so the first 500 million years of Earth history, the Hadean doesn't have any rocks that actually exist from that time period. So the only evidence we have is from zircon grains from places like the Jack Hills. And within the Jack Hills sediment, about 10% of the zircon grains are older than 4 billion years, so come from the Hadean. And in all of the other old rocks around the world, there's a handful of zircon grains that are older than 4 billion years. So there's almost nowhere else on the planet that we can go and really do any science that involves interrogating this first 500 million years of Earth history. And so the Jack Hills is the only place we can go, and the only place we can get, isotopic, geochemical, or in the case of what I've been doing recently, paleomagnetic data from that time.
What is it about that location that makes it such a unique?
That's a very good question, and something that a lot of people argue over. So some people would say there's a preservation bias, so that there were maybe lots of places that had old crustal material. So the idea is you had to have formed some crust to be able to get zircon grains. And, we're lucky at the Jack Hills that those zircon grains got incorporated into a sediment that still exists. So some people argue that there were lots of places like this, and we've just been unlucky and those remnants weren't preserved. And the fact that there's, a couple of zircon grains here and there from places like China and South Africa, other places where there are old rocks, suggests that might be true. And it's just we've just been unlucky in how well they've been preserved. Whereas other people say that, in fact, the early Earth was very different, and there probably weren't very many places that we were producing crust, and so that this actually just happens to be a unique location. It's one of the few places there was any crust at this very earliest part of Earth history, and so it's the only place that it's therefore being preserved.
Okay.
Yeah, it's interesting. So as you mentioned, that segues quite nicely then to some of the work you've been doing about paleomagnetism.
That's true. So there's a big question and a lot of big arguments that have been going on for several years about how we can investigate Earth's magnetic field and how it began. And this is a big controversial subject. So our magnetic field is essentially a big protective shield around our planet. So it deflects really intense solar radiation from the sun around our planet, which protects things like our atmosphere. And so a lot of people would argue that in order to have had life originating on Earth, on a habitable planet, which is what we have, to have a habitable planet with an atmosphere with oxygen in it, that atmosphere must have been protected from quite early on in Earth history. But also to actually form and maintain a magnetic field, certain things must have been going on in the interior of the Earth in terms of what the core looked like and the processes that were going on in there. So people just interested not only in the habitable planet aspect, but also just in terms of early Earth geodynamic processes, are really interested in what that magnetic field looked like. And as I sort of touched upon earlier, the further we go back in time, the less rocks that we have that we can actually go and look at. And also in terms of doing paleomagnetic work, the more likely it is that the rocks themselves have been altered, which would alter the magnetic record as well. And so recently there's been this work trying to use zircon grains, which might have magnetic inclusions within them. So the zircon isn't magnetic, but it might be protecting some magnetic inclusions that were growing in the same rock. And because it's this really stable mineral, it's able to protect them like armor. But also because we can date the zircon, we can say, well, if they've got magnetic information that we can measure and we can get a uranium lead age out of the zircon, we can track directly the magnetic information and put a geological age on that magnetic information. And then you can add in the extra aspect that the zircon record from places like the Jack Hills is even older than any of the rocks that we have on our planet, and therefore we can actually push our information about the magnetic field as far back through time as possible. And that's been the challenge of the project that I've been involved in.
But that sounds also difficult because I guess zircons are small to start off with. So when you're talking about small magnetic inclusions, these must be absolutely tiny.
So when I talk a bit later on, one of the first things that came up about this project, one of the first phrases that was used was that this is the hardest paleomagnetic project that's ever been devised. So for a start, we don't know if there's a magnetic field that far back in time. So we're looking for something that might not be there.
Yeah.
The zircon grains, so they're, as I said, they're accessory minerals. So they're not just a mineral rather than a rock, but they're also some of the smallest minerals that we look at for research. So even just handling those and putting them in a magnetometer to get the magnetic information is very difficult. And then the magnetic signals that they harbour as just a single grain with maybe a few inclusions of magnetic material are some of the smallest magnetic signals that have ever been tried to be measured. And so all of this work that people have been doing recently to look at these single mineral grains and measure magnetic information has come about through the use of a new type of magnetometer, which is able to deal with these incredibly tiny samples and incredibly tiny signals. And those are called a squid microscope, another sea creature analogy, but that's a scanning quantum interference device, which is a very fancy name, but essentially it's a magnetometer. It does the magnetic experiments, so the paleomagnetic intensity measurements in the same way that the old magnetometers would have measured a rock sample, but it's able to do it on these very, very tiny signals.
That's really interesting.
That's so cool.
That's fascinating.
What sort of minerals is the zircon trapping? These tiny magnetic. Is it magnetite? Or?
So for the sake of argument, what we would generally be looking at is magnetite. That's what's going to give you the sort of the strongest magnetic signal for any sort of given terrestrial magnetic inclusion. But there are lots of other minerals as well that might have magnetic signals in there. But obviously the ideal magnetic recorders in terms of magnetite are what we would call single domain magnetites. So that means they've got a single magnetic domain in their structure, which generally means they're going to be very small. So in fact, when we're talking about magnetic inclusions within something like zircon, we're actually probably looking at an ensemble of thousands of nanoscale magnetites that have almost, if you imagine you had a magma chamber with that started to crystallize magnetite within it, and then the zircon grew and captured that magnetite, you would hope it was almost collecting this sort of magnetic dust, and that would then give it the chance of capturing a very strong magnetic signal. Because if you've got nanoscale magnetic particles, they are very stable, so they're very hard to change through geological time. So it's actually better to have tiny magnetic particles than it is to have great big magnetite inclusions.
So metamorphism or anything like that won't, in theory, affect any of this.
So there are two big problems with doing paleomagnetic work as you go back in time. One is reheating the samples.
Oh, right, yeah.
And that's very hard to deal with. Obviously, the rocks that the minerals we're looking at formed in are billions of years old. So they've gone through a huge amount of geological history since they are formed. And if they heat up subsequent to their formation, if they heat up to a high enough temperature, it can reset that magnetic information. So we call that the Curie point. So if you've got magnetite that was cooling in a magma chamber, for example, if it gets heated back up above its Curie point, which for magnetite is around 580 degrees, that magnetic information would be totally reset when it cooled. So that's one problem. So we have to look and find ways of convincing ourselves these rocks haven't been reheated. The other problem is fluid alteration. And this is a really big problem for old rocks. So, over billions of years, we can assess whether or not rocks have been reheated, but there's going to be so much tectonic activity and any fluids that are in the crust, which is totally expected, will reset that magnetic information. And that's really where this project sort of excels, or this type of work excels, because by using magnetic inclusions within other minerals and this idea of armoring the magnetic inclusions, it means that we can kind of take that fluid alteration out of the equation, or we should be able to. It gets much more complicated than that, which is part of the work that I've been doing. But the idea is it's protected from fluids, and then the only thing we have to worry about is reheating, because that information can't have been reset by crustal fluids.
That's really cool. But so I guess in conclusion, then you found evidence of a magnetic field in the Hadean.
Well, I don't want to give the game away too much, but we've done what nobody else has done before, which is to demonstrate exactly what the magnetic particles within these very ancient zircon grains look like But the story then gets very complicated,
Yeah.
and part of that problem is to do with radiation damage. So the zircon grains themselves they contain uranium. That's why we can use them for uranium lead dating. But that uranium very gradually damages the crystal lattice itself. And for most of the things that we worry about, so if you're doing uranium lead dating, for example, that actually doesn't have a dramatic effect. It means that the lead that's obviously no longer bound by the crystal lattice that comes from the decay of uranium, it's sitting in an environment that's no longer perfectly crystalline, and it can move around to some extent, but it generally doesn't go very far, and when it does, we can tell. And so in terms of uranium lead dating, this fact that we've got very tiny amounts of radiation damage in the grains is not very important. It's just an inherent part of working with the material. It's why we can use it as a geochronometer. But when it comes to the elements that shouldn't be in there, so things like iron that can form the magnetite that's important to get our magnetic information, suddenly the tiny amounts of radiation damage that are in there become very important. And that's because we're now interested in nanoscale particles. So our problems and our processes go from being microscale, a sort of normal scale of dealing with our geochemistry, to a whole new level of these sort of nanoscale to atomic scale processes. And that adds in a whole level of complexity that makes it very hard to interpret what the magnetic information means. And the upshot of the work that we've been doing is that it's actually it's very hard to prove that the magnetic information in the grains is primary, and it's almost certain that you can demonstrate that it is secondary, and that the magnetic information is much later than the zircon grain itself. So this sort of holy grail of using magnetic information inside a mineral you can use for uranium lead dating has this total flip side, where because you can use it for uranium lead dating, you can develop microstructures that end up hosting magnetite that's much later than the zircon grain itself. So the whole project has been a sort of first demonstration to take this big arm-waving subject area where it's like, we want to look at how the magnetic field formed and how old is the magnetic field, and we're going to look at this earliest period in Earth history. And what we've been doing is like taking all these arm-waving arguments and actually doing the hard science and saying, this is what you'd be measuring, and this is what that information actually means, and it's probably not what you thought it was.
But then, inside or outside of geology, are there any other methods or techniques you could use for finding out this information about Earth's ancient magnetic field?
That's a really good question, and so I would say no.
Okay.
Could you go to the moon, I wonder?
Oh, so the moon's got its own magnetic
John, that's
history.
your answer for everything, isn't it?
So, with good reason as well.
Yeah.
The moon's great.
So the reason that this project was so neat in the way that it was set up is because we're taking almost the only material you could look at to go this far back in time, and so there really isn't anywhere else to look for that magnetic information. And so what people have done up to this point is to look at the magnetic information hosted with inside other minerals. So not zircon, which we can get an age from. But if we look at magnetic inclusions in, say, quartz and feldspar, which there was some pioneering work done sort of within the last decade, then we can use some of the same assumptions. So we can say those magnetic inclusions are protected, but we then have to go to some secondary information to work out the age of the quartz and feldspar grains, because we can't get an age of those directly. And so people have done that, and so there was some pioneering work done in the US on one of the first squid microscopes, so these sensitive magnetometers, where they were able to push back information about the magnetic field into the Archean, so up to about 3 billion years ago, or a bit older than that, by using those inclusions. But really, the dream was to be able to use this oldest material on the planet, and said once you started to do that, there were these other complexities that arose. And to try and fill in the gap in between those two studies, and so there just aren't enough rocks that you can look at that are suitable enough to try and do this kind of work on. They've all been strongly altered or metamorphosed and reheated. So,
why do you say let's go to the moon, John? Other than vested interest.
I guess I was just thinking that if you could look to see if there's a magnetic field or an early magnetic field on the moon, it might give you an indication as to how magnetic fields start at that sort of time period, and you could then apply that to the Earth.
So this is a big field of research. So the project that we've been doing at Cambridge, which is this sort of characterization project and working out why these things are magnetic in the first place, has a sort of sister project, if you like, being done at MIT in the US, and they're really the paleomagnetic team that's part of this sort of very big project, and a lot of their work is to do with early solar system magnetism. So how you can attract particles to each other in the first place in the early solar system to start to produce like the building blocks of the solar system, so things we now see as meteorites and asteroids, and how the magnetic field in the solar system evolved, and part of that group is also looking at how the magnetic field on the moon evolved as well. And obviously the moon, as far as we know, has its own kind of really unique history in association with the Earth in terms of sort of giant impacts, which obviously is a significant reheating event and sort of almost total destruction event, and so that's got its own unique magnetic record that again has its own very patchy set of rock samples that we're trying to build these big interpretations from.
Yeah, that sounds really cool. So this Pavia Mag project's been quite a recent thing you've been working on then.
Yes. So as I said, most of my background has been on problems associated with uranium lead dating and trying to do a better job of understanding uranium lead age information from minerals like zircon, and
to help us understand the geological record, basically.
And most of what I've been involved in is trying to do that when it gets really hard. So I've been looking at projects to do with the extremes of crustal metamorphism, so when rocks have just got really hot and that starts to make them misbehave in a number of geochemical ways, and uranium lead dating can get quite hard. Or rocks that are very old, and then you start to have other problems associated with how to interpret uranium lead ages, or both. So very old rocks that have got very hot. And so my expertise was in difficult problems with geochronometers, and that's how I got pulled into this project at Cambridge a couple of years ago, to sort of use my expertise in geochronology, accessory minerals, and how to do things when they get difficult in terms of microanalysis and understanding the information, and linking that to something which I'd never thought about before at all, which is how magnetic information is recorded in anything. I knew nothing about that when I started in this project.
That's cool. So would you say uranium lead is your favourite geochronometer?
Yes, absolutely. So, I mean, zircon, which we've talked about a lot already, is, that's really the workhorse of doing uranium lead work, and it's one of the main reasons we have an understanding of anything to do with the ancient Earth at all. I mean, it's one of our main ancient geochronometers alongside argon dating. But in terms of the sheer volume of data in interpreting how plate tectonics works and supercontinent cycles and how early Earth crust was formed and things like that, then uranium lead dating in zircon is really why we know all about that. But a lot of the stuff that I've been doing more recently is looking at uranium lead dating in other minerals that respond to very different processes. So we have other minerals such as monazite and titanite that respond to both high temperature processes like zircon, but also respond to low temperature fluid processes in the crust as well. So we can get this huge wealth of information about what's happening in the Earth crust from everything to do with high temperature crustal processes to how we form ore deposits and things like that. And so definitely I've always been uranium lead person. It's by far the best geochronometer, and there's nothing else that really comes close in terms of understanding the Earth. But there are lots of different minerals telling us lots of different things, not just zircon.
Is that the question you ask when you meet new people, John? You'll be like, hi, what's your name? What's your favourite geochronometer?
It's a very good question.
So, I mean, one thing I think would be really cool to do, so on I don't know if the listeners are aware, but on Twitter there's always a mineral cup where people do these world cups for minerals. I want to do one for isotope systems. I think that'd be
Team Garnet.
niche, but...
I suppose with extreme metamorphism, there must be some cool opportunities for field work, for sample collection.
Yes, that's true. So the project that I was involved in, we had 3 field localities, one of which I specifically worked in, and so my particular area was in South India, which I'd actually worked on since I was doing my PhD. So as I said before, I did this experimental petrology PhD where I made rocks in the lab. But I went to South India during that time to find the sort of equivalent rocks to the things that I was trying to create, and have this parallel study with how natural samples behave. And so that's a good example of some rocks that have got pretty hot. So they come from not very deep in the crust particularly, so sort of normal mid to lower crust levels, but they've been up over 900 degrees. So lots and lots of melting happens in those samples, and we're at the point where we're above what we call the closure temperature for a lot of our isotopic systems. So really, something like uranium lead in zircon, for example, the diffusion of lead out of that zircon can happen at really high temperatures, And then once you get below a certain temperature, that the information gets locked in, and that boundary is at about 900 degrees. So if you're below 900 degrees, you're pretty safe with uranium lead dating in terms of metamorphism. It's fairly easy to interpret or understand the processes. And once you get places like South India, where you're a bit hotter than that, it can start to get much harder. The other two localities that were involved in that project were much more extreme examples of crustal metamorphism, and unfortunately I didn't get to go to those areas myself, but one of those is the Eastern Ghats, which is also in India, and that has examples of rocks from similar depths that get up to about 1,000 degrees. So really temperatures there aren't a lot of tectonic models that we use to understand the Earth that explain crustal metamorphism to those kind of temperatures. And that's got some unique mineral assemblages, for example. So we start to see high-grade metamorphic minerals like sapphirine, and even in some cases a mineral called a sumalite, which are not classic metamorphic minerals, but are real indicators of very high temperatures. Cool. Mm-hmm. And the final area was Enderby land in Antarctica. Oh, wow. And in fact, the samples that we used to do the work in Enderby land were collected over field seasons between 1979 and 1981. So it's actually been very hard for people to get funding to go back to those kind of places.
Yeah, I'll bet. What a unique suite of rocks.
Yeah. So, and in fact, my supervisor from my PhD, even though I didn't work on those rocks when I was working with him, he was one of the people that went on those field seasons back in the late 70s and early 80s and collected those samples, which was pretty daring stuff at the time in terms of getting out into a place that's really not just extreme levels of metamorphism, but pretty extreme places to go and do field geology as well.
Yeah. So the final question we normally ask everyone is, if you could be doing something completely different to what you're doing now, inside academia or outside of it, what would you want to do? Wow.
That's a good question.
I mean, it's probably a hard question because you're already probably doing one of the coolest things in geology anyway. So
I would say one of the things, it's 15 years since I started my PhD, and so I've been doing, a lot of the same stuff for a lot of the same time, for a lot of that time, but there are certainly aspects to the kind of work that I do that I don't really get to do very much, which I would like to do more of. So I found particularly fascinating recently sort of 3D imaging of samples, particularly outside of geology, so 3D imaging of like biological samples and particularly biomechanical stuff. So I would really like to, I guess, if I could do anything as a scientist, I think being involved in those kind of applications that have real implications for people's lives, that would be really nice. Obviously not something you can leap into doing biomedical science from geology. I think probably if I could do anything in the world, I'd probably like to be a helicopter pilot.
Excellent.
Yeah, that's cool.
Well, Rich, thank you very much for coming on the podcast. We'll put a link to your paper about paleomagnetism in Hadean in the description box, so do check that out. But in the meantime, thanks once again, and we'll see you all again next week.
Thank you very much.
Thank you.